Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to continue our lecture on data-based and statistical reasoning. And we left off on objective 4, which is titled probability. Probability is a mathematical framework that's used to quantify the likelihood of events. Now events, they can be classified as independent or dependent, and this distinction is really important in determining how probabilities are calculated. Independent events are those where the outcome of one event does not affect the probability of the other. For example, flipping a coin and rolling a die are independent because the result of the coin flip has no influence on the outcome of the die roll. For independent events, the probability of both events occurring simultaneously is the product of their individual probabilities. Mathematically, that's written in this way. So this expression states that the probability of both events A and B occurring together is equal to the product of the probability of event A occurring and the probability of event B occurring. To illustrate this, let's say we want to flip a coin and we want to roll a die, and specifically we want to flip heads and we want to roll a 6. The probability of flipping heads is 1 over 2 because your coin only has 2 sides, heads and tails. The probability of rolling a 6 is 1 over 6 because your die has 6 faces numbered 1 through 6. Now the probability of flipping heads and rolling a 6 at the same time is 1 over 2 multiplied by 1 over 6, which is equal to 1 over 12. Now, in contrast, dependent events are those where the outcome of one event affects the probability of the other. For example, drawing a card from a deck without replacement changes the probability for the next draw because the total number of cards decreases. Another key concept in probability is the relationship between events that overlap or exclude one another. Mutually exclusive events are events that cannot happen at the same time. For example, when you're rolling a die, the events of rolling a 2 and rolling a 5 are mutually exclusive because the die can only display one face at a time. When we're dealing with mutually exclusive events, the probability of either event A or event B occurring is calculated by summing their individual probabilities. So that's written mathematically here. This expression says that the probability of either event A or event B occurring is equal to the sum of the individual probabilities of event A and event B. However, if the events are not mutually exclusive, meaning that they can occur together, and we want to figure out the probability of either event A or event B occurring, we have to account for the overlap. And this is done using the addition rule, which subtracts the probability of the overlap to avoid double counting. So that's expressed in the following way. This indicates that the probability of either event A or event B occurring is equal to the sum of the individual probabilities of A and B minus the probability of both events occurring together. For example, let's say you have a class, and in that class, 20% of students play basketball. So the probability of students in your classroom playing basketball is 0.2. In addition, 30% play soccer. So the probability of a student playing soccer is 0.3. You also know that 10% of the students in that class play both sports. So the probability of students playing both sports is 0.1. Now, the probability that a randomly selected student plays either basketball, soccer, or both is going to be equal to 0.2 plus 0.3 minus 0.1. And we have to subtract this 0.1 so that we do not overcount. We don't want to double count. We want to account for the overlap in students that play both sports. And this equals 0.4, which means that 40% of the class is involved in at least one of the two sports. Now, the final thing I want to discuss is exhaustiveness. This ensures that a set of events cover all possible outcomes in the sample space. So when you're rolling a die, the events of rolling an even number and rolling an odd number are exhaustive because together they account for all 6 outcomes. And this concept is really important because it guarantees that the total probability of all possible outcomes equals 1, and that's a fundamental rule of probability. Keeping that in mind, let's jump into a practice problem. This problem says, in a certain population, 10% of the population has diabetes and 30% is obese. If 7% of the population has both diabetes and obesity, are these events independent? If one chose an individual at random from this population, what would be the probability of that patient having at least one of the two conditions? Let's start by writing down what we know. We're told that 10% of the population has diabetes. So P diabetes is equal to 0.1. We're also told that 30% of the population is obese. So P obese is equal to 0.3. Finally, we're told that 7% of the population has both diabetes and obesity. So we can write the probability of diabetes plus obesity is 0.07. Now, the first question we're asked is, are these events independent? Two events are independent if the probability of both events occurring together is equal to the product of their individual probabilities. So P, A, and B is equal to the probability of A multiplied by the probability of B. So the probability of diabetes is 0.1, and the probability of obesity is 0.3. And when we multiply these together, we get 0.03. Now, this value is not equal to the probability we were given in this problem for having both diabetes and obesity. Because of this inequality, this shows us that the events are not independent. The occurrence of one condition influences the likelihood of the other. So we answered this first problem. Are these events independent? No, they are not. Now, the second part of this question wants us to calculate the probability of at least one. What is the probability that a patient has at least one of the two conditions? To find the probability of an individual having at least one of the two conditions, diabetes or obesity, we're going to use the formula for the union of these two events. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And this term helps us account for the overlap. Now we're given all of these values, so we can go ahead and plug them in. The probability for diabetes is 0.1. The probability for obesity is 0.3. And the probability of having diabetes and obesity is 0.07. This gives us 0.33. So that means that the probability that a randomly chosen individual has at least one of these two conditions is 33%. And with that, we've solved this problem and we've completed objective 4. Our next objective deals with statistical testing. Statistical testing is a powerful tool that allows us to determine whether the results of a study are due to chance or reflect a true effect. This process revolves around evaluating a hypothesis using mathematical reasoning. And at the heart of statistical testing lies the idea of the null hypothesis and the alternative hypothesis. The null hypothesis is a statement of no effect or no difference. It assumes that any observed variation in the data is purely due to chance. For example, in a clinical trial, the null hypothesis might state that a new drug has no effect on blood pressure compared to a placebo. On the other hand, the alternative hypothesis proposes that there is an effect or there is a difference. This can be directional, where we predict the direction of the effect, so we can say, hey, the drug lowers blood pressure, or it can be non-directional, where we simply predict that there is a difference without specifying its direction. The goal of statistical testing is to decide whether to reject the null hypothesis in favor of the alternative hypothesis. And to make this decision, we calculate a p-value, which quantifies the probability of observing the results we obtained if the null hypothesis were true. In most studies, a p-value is compared to a predefined significance level, often set at 0.05. If the p-value is less than the significance level, we reject the null hypothesis and we conclude that the results are statistically significant. So for example, if we find a p-value of 0.03, this means that there is only a 3% chance that the observed results occurred under the null hypothesis, and that leads us to reject the null hypothesis. However, it's important to note that rejecting or failing to reject a null hypothesis comes with risks of error. And these errors are categorized as type 1 errors or type 2 errors. A type 1 error occurs when we reject the null hypothesis, even though it's true. This is also known as a false positive. So for instance, concluding that a drug works when it actually doesn't, that's a type 1 error. A type 2 error occurs when we fail to reject the null hypothesis, even though it's false. And this is called a false negative. So for example, concluding that a drug has no effect when it actually does, that's a type 2 error. These errors are really important to understand because they highlight the balance between statistical power and the probability of making mistakes in hypothesis testing. Statistical power is the probability of correctly rejecting the null hypothesis when it is false. Increasing the sample size or the effect size, that can enhance statistical power, which can reduce the likelihood of type 2 errors. Now, another important concept in statistical testing is the confidence interval. This provides a range of values within which we expect the true population parameter to lie. Now, wider confidence intervals indicate more uncertainty, while narrow intervals suggest greater precision. Confidence intervals are closely tied to hypothesis testing because if the interval excludes the null value, then the results are considered statistically significant. Now, to take all of this and summarize it, let's use this table right here. When you're conducting a hypothesis test, we either reject the null hypothesis or we fail to reject the null hypothesis. If we reject the null hypothesis when it's actually false, we make a correct rejection. If we fail to reject the null hypothesis when it is true, we make a correct acceptance. However, if we reject a null hypothesis When it is true, then that's a type 1 error. And if we fail to reject the null hypothesis when it's false, then that's a type 2 error. And with that, we've completed objective 5, and now we can move into objective 6, where we're going to cover charts, graphs, and tables. Visual representations of data are critical for summarizing large amounts of information, identifying trends, and communicating findings effectively. Each type of chart, graph, or table has specific applications, so understanding their purpose and learning to interpret them correctly is essential. Let's start with discussing pie charts, also known as circle charts. Pie charts are particularly useful for representing relative proportions of a whole. For example, in a survey about preferred transportation methods, a pie chart could display the percentage of people who walk, drive, cycle, or use public transit. These charts are especially popular in demographic studies because they clearly show how categories contribute to a total. Bar charts, on the other hand, are ideal for categorical data. Categories are represented on one axis, while the frequency or value of each category is shown on the other. For instance, a bar chart might display the number of students in different academic majors at a university. Also, bar charts are particularly effective when comparing quantities across discrete groups. Now, when we want to examine the distribution of numerical data, histograms are the tool of choice. So unlike bar charts, histograms group data into intervals or bins, making them useful for identifying patterns in continuous data. For example, a histogram of students' test scores might reveal whether the scores follow a normal distribution or are skewed. Histograms are also helpful for identifying the mode. This is the most frequently occurring value in a data set. Another valuable tool for examining data distribution is the box plot, also called a box and whisker plot. Box plots summarize data by showing the range, the median, the quartiles, and the outliers. For instance, a box plot of monthly sales figures could quickly highlight variability and even identify unusually high or low values. The interquartile range, represented by the box, captures the middle 50% of the data, while the whiskers extend to the minimum and maximum values within a certain range. Now, maps. These are another way to visualize data, especially when comparing geographic or demographic information. A population density map, for example, could display the number of people per square kilometer across different regions. Maps are especially useful for understanding spatial relationships and regional variations. For relationships between variables, line graphs are commonly used. A line graph connects data points to illustrate trends over time or other continuous changes. Depending on the data, these graphs can take on different forms. Let's start with discussing linear graphs. Linear graphs represent relationships with a constant rate of change, and they appear as straight lines. They're described by the following equation: y equals mx plus b, where m is the slope and b is the y-intercept. The slope is calculated as the change in y over the change in x. These graphs are commonly used to model situations where one variable changes at a consistent rate relative to another. Then we have parabolic graphs. These depict quadratic relationships, and they form U-shaped curves called parabolas. They're described by the equation y equals ax squared plus bx plus c. Now, parabolas can open upwards or downwards, And these represent scenarios like the trajectory of a projectile under uniform acceleration. Next, we have exponential graphs. These illustrate rapid increases or decreases, and they're characterized by equations like y is equal to ab raised to the x. B here is the base of the exponential function. These graphs are prevalent in modeling growth or decay processes, such as population growth or radioactive decay, where changes accelerate over time. Next, we have logarithmic graphs. These graphs represent relationships where the rate of change decreases over time, and they're described by equations like y equals a log x plus b. They're really useful for scaling data that spans several orders of magnitude because they compress large ranges of values and make it easier to analyze data that grows or shrinks rapidly. Now, here we can also talk about semi-log and log-log graphs. Semi-log graphs are graphs where one axis is scaled logarithmically while the other axis remains linear. And log-log graphs have both axes scaled logarithmically. Now that we've discussed these various graph types, let's talk about tables. Tables are another means of presenting data. On the MCAT, tables are commonly used to display information in an organized way, often combining numerical values and categorical labels. When interpreting tables, the focus should be on identifying patterns, trends, and extracting key details that are relevant to the question being asked. Now, when you're dealing with tables on the MCAT, keep the following tips in mind. First, read the title and the labels correctly. The title often explains the purpose of the table, while the row and column labels provide context for the data. Misinterpreting these can lead to incorrect conclusions. Second, focus on the variables that are relevant to the question. Many MCAT questions involve identifying trends or relationships in specific parts of the table. Highlight or mentally note the rows or columns that are directly related to the problem. Then third, look for overall trends. Scan the table for patterns like increasing or decreasing values, and these trends often form the basis of test questions. Finally, avoid overanalyzing irrelevant details. So tables may include extra information to test your ability to focus only on what's important. So stay aligned with the question stem and save time. With that, we have completed everything we need for Objective 6. Now we can move into our last and final objective, which is titled Applying Data. This involves understanding the relationships between variables and correctly interpreting their implications. In particular, we're going to focus on correlation, causation, and the critical distinction between the two. Correlation refers to a connection or relationship between two variables. This relationship can be direct, where both variables increase or decrease together. It can be inverse, where one variable increases while the other decreases, or it can be more complex than that. Correlation is often quantified using the correlation coefficient, which is a value between -1 and +1 that describes the strength and direction of the relationship. For example, a correlation coefficient of +1 indicates a perfect positive correlation. A correlation coefficient of -1 represents a perfect negative correlation, and a correlation coefficient near 0 suggests no meaningful correlation between the variables. Now, it's important to remember that correlation does not imply causation. A strong correlation indicates that two variables move together, but it does not establish that one causes the other. For example, there might be a strong correlation between ice cream sales and drowning incidents, but this does not mean eating ice cream causes drowning. Instead, a third variable like hot weather might influence both. To determine causation, we turn to Hill's criteria, which provides a framework for evaluating whether a causal relationship is likely. These include factors like strength of the association, consistency across studies, and the elimination of alternative explanations. Even with these criteria, establishing causation often requires experimental data and careful analysis. Another key point when applying data is distinguishing between statistical significance and practical significance. Statistical significance means that the results are unlikely to be due to chance. And this is based on a predefined threshold like the p-value is less than 0.05. However, this doesn't always mean that the findings are meaningful in the real world. So when you're interpreting data, always consider the context of the hypothesis and existing scientific knowledge. Ask yourself, are there alternative explanations for the observed relationship? Is the effect size large enough to matter in practice? And does the evidence align with prior research? By critically analyzing data and distinguishing correlation from causation, you can avoid common pitfalls in reasoning and drawing accurate, meaningful conclusions. This skill is really essential not only for interpreting scientific studies, but also for applying data effectively in the real world. And with that, we have finished our last and final chapter in this playlist. Again, I'm so proud of you for making it through. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.